at a high level, the two-way ANOVA is exactly like the one-way ANOVA with one exception. So remember our one-way ANOVA, we had our continuous variable, our dependent variable, and we had one independent variable with two or more levels. So the difference between that and a two-way ANOVA is that you have two independent variables instead of one. So we're looking at how two different independent variables impact our dependent variable. So that is a two-way ANOVA. That is literally the only difference, and we run it a little differently as well. So you can also, and I'm not going to go over all the details of this two-way ANOVA example because there's a lot here. There's extra information on this website of some of the things that I don't have time to go over. And the example, just to cite my source, comes directly from this website. This in general, www.sthga.com is one that I use very frequently, both for programming and for statistics. It's a very good website. I really like it. So if you want to follow, you can follow in my code, or you can also follow on this website step by step what I'm doing. Like I said, I have to skip some stuff just because of time constraints. The things that I'm skipping, we will be reviewing when we go over correlation and simple regression. Most of those things are in both. So we have our two independent variables. So in this case, I'm going to use base R has a bunch of data sets preloaded into it. One of the one that's very frequently used when showing how to use machine learning models is the iris data set. This is one I actually didn't see until this time. It's called tooth growth. It's a little bizarre, to be honest, but they put it in there specifically to show how to use this kind of test. So that data set, tooth growth, we are comparing the effect of vitamin C on tooth growth in guinea pigs. No idea why they included this, but it was kind of a fun example, something that none of us probably know anything about. So in this case, independent variable 1 is the dose of vitamin C, and that should say vitamin C here. So the dose. So it's 0.05, 0.5, 1.0, or 2.0. Now our independent variable 2 is going to be the form of vitamin C, either absorbic acid, which you'll see if you take a vitamin C supplement, like a pill, it'll be put in there with absorbic acid almost all the time, or through orange juice. So our dependent variable is going to be the length of odontoblasts, basically the length of the tooth or the cells responsible for the tooth growth in the guinea pigs. Don't ask me what that is. I don't know. But it works great for this particular example. So now I'm just going to walk through it directly in R. I didn't walk through these in the slides step by step, but it's explained very thoroughly in R. Before I go on into the code, like I had told you guys before, in a lot of cases, I visit a lot of websites when I prepare these slides and compare how other authors explain these things, try to find the best explanation, and then use similar words. I'm trying to learn how the best way to explain these results is. So when I found a really good website, I just stuck it on the slide. So if you can come back to that or not, totally up to you. There's more detail here. So now I'm going to go through this step by step in the code. So our two-way ANOVA. So this is already loaded into R, since it's a built-in data set. So all we have to do is assign it to a value. You could also use tooth growth itself, but I'm going to assign it to tooth.df. So first, let's look at our structure. So this is what you would expect. We have our length. So this is our dependent variable. Our supplement, so that would be orange juice or absorbic acid. Absorbic acid is a VC. I'm not sure why. There's probably some scientific reason for that I don't know. And then our dose. So this is going to be 0.5, 1.0, and 2.0. You're going to notice that this is a numeric variable here. we're actually going to convert that to a categorical. So since it is basically just 3 different values, that's why you can use this as a categorical variable. If it was continuous between 0 and 10 and had a bunch of decimal points and they were all different, you would not be able to do this. So I'm taking our levels, 0.5, 1, and 2, and I'm assigning them to D, 0.5, D1, and D2, because they're Oblast or whatever. So, and our dose. So I think this refers to dose 0.5, dose 1, and dose 2. So we're creating that factor variable. The other reason you want to do this is because you want this to be our lowest value, this to be our middle value, and this to be our highest value. So we're creating that factor variable. Now let's rerun our structure. We're seeing our previously integer value is now a factor. So the next thing we would probably want to do is to make sure one of the other assumptions is that if you have really unbalanced data, so here, we're seeing that in each cell of our data for our ANOVA, there are the same number of values. If you saw 2 here and 50 here and 30 here and 100 there, you would have a problem. You couldn't run the ANOVA, but that's something else that you should keep in mind. But here it's equal, so we're good to go. There is a specific test that you can run for unbalanced data. I would recommend looking that up if you run into that problem. So the first thing I told you before is to run these box plots. So we have 6 box plots here since we have 6 variables that we're looking at. So our blue ones are our supplement type. So we are OJ and our VC, absorbic acid. And then we're seeing our dose values down here, and we're seeing how those 2 values relate to our length. So we're seeing that these are pretty distinguishable. They're pretty different from one another. So that's going to matter when we run our test, and it'll give us a good idea of whether our results make sense by coming back to look at that. Also, no very extreme outliers here. If I have a problem with normality, I can come back to that. But I don't think, given my domain knowledge, that there is going to be an outlier problem. So next thing, I thought this was a very interesting thing that they did on the website. It actually did, since dose is ordered, when you have an ordered variable, you can make a line graph here, and it gives you some pretty useful information. These are error bars. So that would be the error in our data. And you can see that they're grouped by color and by dose here. So you can also see very clearly using that our values or our tooth length is increasing as our dosage increases. So there's a much bigger increase between dose 0.5 and dose 1, and there's a smaller increase between dose 1 and dose 2. So that we'll have to keep in mind to see if our results make sense later on. So we're going to run that ANOVA. So we're seeing here that there at least 2 levels of our dose. So we're seeing this is significant here. So at least 2 levels of our dose variable, so they have 3 levels, are significantly different from one another. Our supplement only has 2 levels. So we know that both of those levels are significantly different from one another. We're seeing that with our p-value. So going back, our sum of squares is going to describe our variation. For our supplement, it would be between the supplement groups would be our sum of squares. And this would be between our dosage groups, and this would be within those groups, so the error value. Our mean squared error is going to be using the sum of squared divided by our degrees of freedom, and then that's our mean value. So here we're taking our sum of squared divided by 2. That's going to be this 1,213 value. And down here we're taking our sum of squares within groups divided by our degrees of freedom, and that's our mean squared error here. So you'll remember that. Now our F value is our mean squared between groups, as you remember. and that would be divided by the mean squared error. Same here. So our mean squared between our doses, 1,213, divided by our mean squared error. That's what's going to read out these F values. The bigger these F values, the better. You can think of it as there's more difference between groups than there is within groups. So that shows you that our groups are more substantial or give us more information than our error does. So when we're seeing that these two values are high, these groups are highly significant. But remember, in the dose, we don't know if the dose 0.5 is significantly different from dose 1, or if dose 1 is significantly different than dose 2. So we have to run that extra model here. Are there any questions about that? Okay, running through this one faster, just because I think that hopefully that first one gave you some idea. I did forget to put this in the slides. So there's something called an interaction effect. This is really useful. So when we look at this interaction effect, and I do think that they may have put a visualization on the website that I recommended here. So we're going to look at our interaction. At first, when we computed it, it did it without an interaction. So if you wanted to do a ANOVA without an interaction, you would use a plus sign. You're going to see that difference down here. So we're looking at our interaction effect. So you're putting a multiplication sign here. So what does that mean? So you can see down here, it's going to give you a good idea of what an interaction effect. So when we're looking at them separately, they're called a main effect. And the interaction effect is kind of how they work together. So going back, let's look at this. So we would, when we're looking at an interaction, and this is always something that's a little difficult to explain, so I'm going to do my best. So an interaction effect, if we're looking at it with a main effect at one variable at a time, all that tells us is that the dose 0.5 is different than dose 1, and so on and so forth. However, when we look at the interaction, it uses both of these variables together. So it includes the interaction between these two. So our doses, as well, combined with our supplement type, is this group significantly different than this group? The best way, or how do they work together, or how do they affect one another? So that I always have a hard time explaining this. So one time I was in a meeting and I struggled with explaining this then. So somebody from my team actually came up with a really odd example that I was never aware of. So I think most of you are of age and probably had beer at some point in your life. So according to this person, I think it's probably an old wise tale. You all may not agree with me. So, but I didn't notice a difference at all, but I'm not a big soda drinker. So he said that, say you drink 3 beers and you also have 2 sodas. He says, now if you drink those 3 beers, you're not going to be as you're not going to be as drunk, for instance, or as buzzed as if you have 3 beers with 2 sodas. So it basically, the interaction effect is basically it's having 3 beers at the same time as having those soda along with at the same time. Are you going to end up being more drunk when you drink them together or when you drink them separately? I don't know. I kind of think that that's an old wise tale, but that gives you an idea of how an interaction effect works. So is beer separately gonna be different than beer and soda together? So hopefully that helps, and given without that definition. So we're gonna look at that interaction effect. We're looking here. So we're seeing that our interaction effect is below 0.02. That means that supplement and our dose type are working together in their interaction. So the combination of those two is significant. Think of the soda beer idea. So we're going to just real quick run some summary statistics. If you look here, if we're trying to figure out if that makes sense, we can look at this OJ. That's 26. VC doesn't look much different here. However, if we're looking at the dose 1 and dose 2, whether you do OJ or the absorbic acid, there's a pretty big difference here. And you also see a pretty big difference between those rows. So that makes sense. Our result makes sense. So now, as I said, if you go up here, our supplement, so OJ versus absorbic acid, only 2 levels, so you know exactly what is significantly different than the other value. But we have 3 levels here, so we don't know whether dose 1 is significantly different than dose 2, or if dose 0.5 is different than dose 1. So now we can run our Tukey's HSD test. I think I'm going to go a little over today, but since I don't have a room reserved, so hopefully that's okay, feel free to log off. So we're running our Tukey's HSD test, and I did choose the one with the interaction variable here. So we are going to look at specifically the dose variable, since we had 3 levels. So down here, we ran that. And our difference here, 9.1, is statistically significant. So our difference between dose 1 and dose 0.5. So they are significantly different. The difference in means is significantly different from one another. Now we're looking at dose 2 and dose 0.5. They're obviously significantly different given what we're seeing here. Now we're looking at dose 2 versus dose 1. It is also significantly different. And all of those p-values are very small. So we can be very confident in these results. So the next thing that we do, we need, in order to make sure that these results are right, we have to check our assumptions. So first, we'll remember we did this before. We're seeing more of a randomness here. So we're looking at our different values. We're looking at our fitted values versus our residuals. You're seeing more columns here, remember, because we have that interaction variable. So it's going to affect our predicted values and have more than, say, three vertical lines here. So that's why you're seeing more data and it's spread out differently. So these are our predicted values and our residuals are our error. So we're seeing the outliers aren't, this one would be one that you would want to be cognizant of, and this one as well. If our tests are showing that these need to be removed, you would probably want to do so. We'll see. So first, let's check the homogeneity of variances. It's 0.14. That shows us that our variances are not significantly different from one another in any of our groups here. So that's good. We can assume homogeneity of variances. Now, we're looking at our normal QQ plot. So here it's following a straight line. So that's a good sign. That means it may be normally distributed based on that value. So now to check this normality numerically, as we did before, we'll run the Shapiro-Wilk test. So we're assigning our residuals from our model to this object, running that. And now we are going to run on those residuals a Shapiro-Wilk test. So here, our p-value is 0.66. So our residuals are showing that our data is normal. Given that I see this, the outliers that I saw here are probably not a big deal. They're not far enough out to affect our results, especially because we're seeing such a high p-value here. So now that we have that piece of information, don't worry about those outliers. So we've looked, again, checked off our boxes. So our values are independent from one another. The experiment was set up to do it that way. Our data is normally distributed. We don't have significant outliers, and our variances, we have homogeneous variances, or our variances are equal. So given all 4 pieces of information, if we now can assume that our ANOVA results, that these are valid results, and we're seeing a true effect here, especially because of these low significant values. So that is ANOVA. Again, just to recap, just as we saw here, this was a very specific setup research experiment, very odd one, but this is how you would use it in an experimental setting.